Thank you. Today I'm going to look at DOT culverts, the many thousands of DOT culverts, through two lenses: climate, which we used to call hydrology and hydraulics, and environment, more commonly known to us anyway as fish passage. We've been dealing with the idea of resilience for a number of years now. This order from Federal Highway Administration goes back to 2014, and it was direction from Federal Highway that we needed to look at the resilience of our transportation systems. In particular, I'm interested in the ability of our culverts to withstand these extreme weather events that are commonly known as design flows, the Q50s, the Q100s. So when it comes to resilience, I'd like to know, does our existing culvert hydraulic design standard deliver resilient culverts? And then looking at all those many thousands of culverts we have in the ground now, how resilient are they? And then finally, when we do replace a culvert with something that allows for fish passage, how resilient is that fish passage culvert? We categorize our hydraulic structures at DOT by size. We have bridges, 10 feet and bigger, and we have about 2,500 of those. Large culverts between 5 feet and 10 feet, about 2,000. And then cross culverts, nearly 36,000 of them. Those culverts smaller than 5 feet diameter or width. And I'm going to focus on cross culverts. Okay. They tend to not get much attention. They don't get much respect. They tend to fly under the radar. And yet, by sheer numbers, they can be big problems for us. Traditionally, we view cross culverts as small, simple, and cheap. Very little, if any, design would go into them. We'd replace in kind. They might have been sized by somebody's rule of thumb. And only if there was a known hydraulic problem would we make them bigger. Now, as we size things for fish passage, some of these small culverts have become very big. Causes a great deal of heartburn for us. And then now, with more attention paid to resilience and climate change, we are doing hydrology and hydraulics for many of even our smallest culverts. And many of these small culverts are being captured in the hydraulic design standard and being upsized as a result. This is our cross culvert population in Maine. We have about 36,000 of them, 29,000 2 feet and smaller, 7,000 between 2 feet and 5 feet. I assume that most of those 29,000 are stormwater conveyances. Probably only a relative handful carry what might be called real streams that flow at least part of the year. On the flip side is, I would assume that most of those 7,000 culverts between 2 and 5 feet are probably carrying real streams that flow at least part of the year and might potentially be candidates for fish passage. Now, why is culvert upsizing a problem for us? Simple answer is, if it's going to get bigger, it's going to cost more. But if we're only talking about going from a 2 or 3 foot pipe to a 4 or even 5 foot pipe, that's not such a big deal. This sort of incremental upsizing, usually due to correcting for the hydrology and hydraulics design standard, is manageable. We can design for it, we can budget for it, not a big deal. But if we're going from that same small pipe to a large box culvert for fish passage, that is a huge deal for us. Costs could go up by a factor of 5 or 10. Now, on a year-to-year, project-by-project basis, we deal with it, but we don't have a good feel for overall system requirements, overall system exposure to this sort of upsizing. So, can we capture this exposure over many thousands of culverts? Yes, we can now with modern GIS tools, web tools for hydrology and hydraulics and watershed analysis. So for starters, how resilient is our culvert hydraulic standard? Do we get resilient culverts from this standard? Our culvert hydraulic standard is a bit of a two-headed monster because of these two categories of culverts, cross culverts and large culverts. In the old days, we had a single hydraulic standard for both categories, but not anymore, and that's a different story. Cross culverts, because we think of them as being small and simple and cheap, they have a less stringent design standard. We design for a 50-year flow, and we allow submergence at the inlet to surcharge the inlet by as much as 50% of the size of the pipe. On the other hand, for large culverts, we design for a slightly larger flow, the 100-year flow, and we don't let the water surcharge the inlet. We don't let the water get any deeper than the top of the pipe at the inlet. This is a simple illustration. You can see that for the large culvert, LC, the water can only go up to the top of the pipe at the 100-year flow. Very often it will be less than that by some amount. Whereas for the cross culvert, we designed for a smaller flow, 50-year flow, Q50, and the water can go above the top of the inlet by as much as 50%. As a result, for the same watershed, if the cross culvert hydraulic standard results in a smaller pipe than the large culvert hydraulic standard. So how do you look at thousands of cross culverts? Well, we have to keep it simple. And thankfully we can do that. We have simple hydrology. We have a very simple statewide regression equation for design flows, where you can calculate a design flow based only on the watershed area. Likewise, you can calculate a bank full width, if you anticipate fish passage, just from watershed area. And then simple hydraulics, we can calculate a pipe size for a given design flow just from watershed area. Now, do you get watershed area? Stream stats. But of course, instead of looking at these culvert by culvert, we're processing hundreds at a time. But this is the same tool I'm sure you're all familiar with. It's a great tool, and it delivers just what we need. This is what the regression hydrology looks like. Again, I told you it was simple. Plots up as a straight line on a log-log plot, watershed area across the horizontal axis, the design flow on the vertical axis. What I want you to get out of this graph is that the 100-year flow isn't much bigger than the 50-year flow. 100-year flow is only about 20% bigger than the 50-year flow, and the same when you compare the 50-year to the 25-year. So you could use this graph as it is to get a simple estimate of design flows based on watershed area. What about future flows? We still don't have a reliable, acceptable method for projecting future design flows, and so until something better comes along, I just assume a 20% increase by the end of the century. Now, I didn't pull that number out of the air. It's based on some precipitation work done for New York DOT. It's simplistic. I believe it's reasonable, but also overly conservative. So until something better comes along, this will work. Now, this is hydraulics. This is a culvert hydraulic performance curve. Without going into the mathematical details, this is what allows us to go from watershed area to a pipe size. That one curve. When you solve the equations, you come up with two simple equations, one for the large culvert standard, one for the cross culvert. The result is that for a given watershed, the large culvert is about 30% bigger by diameter. 20% of the 30% is due to the more stringent inlet submergence standard. The other 10% is due to the fact that in a large culvert, we design for a slightly larger flow. This graph, I know it's busy, I apologize, but it summarizes this idea that you can size a pipe just from watershed area. A couple of things I'd like you to take away from this. First of all, in the middle of the graph, you can see that yellow upward arrow. That shows the jump from the cross culvert standard to the large culvert. Slight increase in size as you go from the cross culvert into the large culvert. The brown line is the bank full width as a function of watershed area. So a couple of simple comparisons here. If you're sizing a half a square mile watershed, you would come up with about a 4-foot diameter pipe. But if someone said you had to provide fish passage and make it bank full width, you would have to provide something 8 feet wide. It's a big difference. That pipe is twice as large. Okay. Another thing to take away from this, our cutoff for going from a round pipe to a box culvert is 8 feet. Anything bigger than 8 feet will tend to be a box culvert. So if you're sizing for fish passage, bank full width, you have to start building box culverts at watersheds of about half a square mile. But if you're only going by hydraulic sizing, you can use round pipes up to about 2 square miles before you have to start building box culverts. And that switch from round pipe to box culvert comes at a significant increase in cost. Last thing to show here is this difference between existing hydrology, Q50 and Q100, and projected hydrology of being 20% bigger. So for cross culverts, that's the blue line and green line, large culvert, red line and yellow line. Not much of a change there in pipe size. And so my suggestion based on this is that design to a good standard using current hydrology, and don't worry about projecting peak flows in the future. Perhaps 10 or 20 years from now, we might change that guidance, but for now, that's good guidance. Last thing over on the side, I just show some upsizing ratios. You can see that bank full width sizing about doubles the width of the required structure. Last comment about bank full width sizing. The bank full width structure has capacity far in excess of the required Q100 capacity. And it's only for the very largest box culverts where the hydraulic standard starts to converge to the box culvert flow capacity. And so if you're sizing for fish passage, we have plenty of excess capacity, plenty of resilience. It's not something to worry about. So conclusions, our hydraulic standard provides sufficient resilience against future flows, as well as existing hydrology. And fish passage bank full width sizing provides excess resilience, excess capacity, but at a large cost. Now, what about our existing culvert population? I'm going to limit this just to part of the state, our MaineDOT Region 5 in Aroostook County, up in northern Maine. We have about 6,000 cross culverts there. About 2/3 of those are 2 feet and under, 1/3 between 2 feet and 5 feet. And I'm going to break these sizes up into 3 categories: less than 2 feet, 2 feet to 3.5, and 3.5 to 5 feet. And I'm going to look at hydraulic sizing standard and bank full width sizing. So for this first category, 2 feet and under, when I apply hydraulic standard to these watersheds, yes, we upsize, but it's modest upsizing, something that's very manageable, something we can live with. Only a handful get upsized into the large round culvert size of 7 or 8 feet. We can live with this. On the other hand, if we have to do bank full width sizing for these same watersheds, we end up with 37 box culverts as well as 100 very large round pipes. If you had planned on replacing with a 2 or 3 foot pipe and instead are faced with a large box culvert, this is a shock. This is startling. And we don't plan for this. And we still don't know how we deal with this on a system-wide basis looking out over the years. Instead, we respond on a year-by-year, project-by-project basis. This is frightening. Next size, 2 feet to 3.5 feet. Again, hydraulic upsizing for the hydraulic standard, something we can definitely live with. We get 1 box culvert, a few large round pipes. This is good. But if we size for bank full width, we have 100 box culverts plus another 150 large round pipes. This is bad. Finally, the last size category, 3.5 to 5 feet. Again, applying the hydraulic standard, we upsize. Yes, we have a certain number of large round pipes. That's to be expected because these larger cross culverts are on larger watersheds. But again, we can live with this. But if we size for bank full width, out of 276 culverts, we have 65 box culverts and another 40 large round pipes. Again, this is startling. This is overwhelming. So to conclude, I would say that our hydraulic design standard produces resilient culverts for existing and future design flows. We can manage our existing culverts for resilience. When it comes time to replace, we can upsize by the hydraulic standard and live with our budgets. But when we have to upsize for fish passage, we get lots of redundant resilience, but at the cost of severe funding and program management challenges. Thank you, and I'm happy to take any questions.